All right, so yeah, I know that I've met each of you, but old habits are hard to break. So Michael Henry, I'm here from Pacific Northwest National Laboratory. I have a joint appointment here at Texas A&M, currently working out at the Rellis campus, doing a variety of different activities, teaching a class for some commerce students, doing some work in this human machine ecosystem laboratory, and looking for ways to create connections across P&L and A&M. So the purpose of my talk today is just to give an overview of the type of work that we're doing at P&L and to hopefully foster some sense of like, okay, here's what some collaboration opportunities may look like. As a national lab, we've got an applied science mission, but we also do some basic research. We have plenty of opportunities to engage with academia, to bring faculty and students in on some of our sponsor problems, to go after some hard research types of activities and jointly funded work. And I'm here not just, I have a mandate to build a closer relationship between A&M and P&L in the same way that A&M has enjoyed, from what I understand, like a very fruitful relationship with Lanel and Sandia and some of the other labs. You know, P&L has done some work here, not on the data science, math, or computer science side, but in some other areas. And I'm here to be a connection point. So brief background on me, I have a bachelor's in computer engineering from Purdue University and a master's in computer science from Georgetown. I don't have a PhD, although I guess technically here I'm on campus, so maybe I should rectify that one day. My research background, the first analytic work that I had done beyond some software engineering stuff was in machine learning and audio data. I've done mostly computer vision related work. I'm very interested in building representations of media for large scale retrieval problems. I've also been interested in GANs lately. And I also do some work, just general large scale analytics, cyber analytics, natural language processing. I touch on a lot of areas, and I'll touch on a lot of areas here too that we do at P&L. I cannot like fully represent the full depth of each of these things, but I can provide content and context for other folks. Or I could provide other people who can have those conversations. So if you're not familiar with the National Lab System, there are 17 Department of Energy National Labs. They're basically broken up into these 4 categories. You've got the NNSA laboratories like Sandia and Los Alamos. You've got the energy labs like Idaho. And then you have DOE Office of Science Laboratories, which P&L is one of those. Are any of you familiar with the DOE OSCAR computing program? OSCAR is an Office of Science program. P&L participates in that as well. OSCAR, I bring up OSCAR just because of the Office of Science connection. OSCAR has really close relationships with like Lawrence Berkeley and Livermore and Oak Ridge due to their high performance computing systems. P&L doesn't have those types of that scale of system. We have our own HPC, but nothing like that. We are more of an analytics lab. And we are also smaller than some of the other labs. Like Sandia has something like 14,000 people. We've got a little over 5,000. So that's the scale that we're working with. So there's a breadth of sponsor missions that we support all across the government. We're a multi-program lab, which means that we don't receive block funding from the Department of Energy to do our work. We partner with different elements within the government to conduct our applied research. And so about half of which is direct, well, actually more like 2/3 of which is direct DOE work, and then other partners within the government make up our other funding. Like I said, we have about 5,000 staff. We publish, although not as much as like an academic institution. If you look me up on Google Scholar, you'll see 1 or 2 papers a year for the last couple of years, and my name at the end of the author list more so than at the beginning. So that kind of gives you a sense of what we do. We also, envision disclosures and all that sort of stuff. So being as a Department of Energy National Lab, we have core competency areas that the Department of Energy identifies as being things that they look to Pacific Northwest National Lab to do. And these cross a number of different science and engineering areas, from biological neurosciences to chemical materials engineering, but also, and the focus of this talk, our work on the computational mathematical science side. So within there, we look at these 5 areas: advanced computer science, viz and data, computational science, applied mathematics, cyber and information sciences, and decision science and analysis. These are our areas that we view ourselves as having expertise in. But how that translates in a more concrete way is we our strategic elements, the way we spend our own money in our lab directed research and development funds, go towards advancing our capabilities in these areas. That doesn't mean that we can't go outside of these whenever we have the right partnership or the right program, but you're never going to see P&L, at least in the time in the near future or in any point in its past, invest $10 million in like a robotics program. Like, that's not us. That's not what we do. If you need to do robotics, then there are plenty of other folks that can do that. All right, so working with P&L, we are a federally funded research and development center. This is relevant only in the sense that as we explore potential partnerships for us to go after, there are certain restrictions on FFRDCs through some sponsors, like DARPA, for example, will say that an FFRDC can't prime a response to one of their programs. It's very common with them. Most of the time, the university then takes the prime and subcontracts out to P&L for some specific aspect of that. We are a public-private partnership. We're managed by Patel, which is a not-for-profit based out of Columbus, Ohio. We're full cost recovery, which means that we bill for time. It restricts the types of contracts that we can go after. And one thing that's really nice in that we sit in this region between like pure academia, pure public, pure private enterprise, is that we have a lot of folks, a lot of staff at the lab who are very academia minded. Like, these are, whether they're, fresh PhDs out of a program, or maybe they worked in academia for a while and they come work at the lab, or they just have that mentality of collaboration that comes with working with the university. We have plenty of people who, if you ever want to have a phone call with somebody, this is not, we're not to set up a contract, we're not to like do a weird thing. You just tell me that you want to talk to somebody, and I put you in contact and you have a conversation. It's very easy to have that, and it fosters a lot of opportunities for proposal writing and all that sort of stuff. So internal to the lab, we have something called Lab Directed Research and Development, our LDRD program, where basically through every dollar that we get through sponsor funded work, we take a little bit of that and we put it into a pool of money called LDRD, and we use it to build out early stage research efforts that could potentially lead to larger programs down the line. As an example, I had what we call an seed LDRD back in 2015, where I was looking at that essentially we were looking at methods for interrogating social media data. So we had a bunch of social media data around climate change, climate protests, that sort of stuff. And convolutional neural networks were really gaining steam back in 2015. So we're like, let's take some embeddings out of convolutional networks. Let's look at some recurrent neural networks, which were the thing back then, and all that. And let's see if we can learn some like joint understanding of these two data modalities back then. It's kind of a vague problem. It was Back then, it wasn't like a solid thing. Like right now, I could download something off a Hugging Face that would do what I was trying to do, but that back then it was kind of new. And it was an opportunity for us to, like, we trained a bunch of our staff in deep learning. We, published like a little bit, but not too much. Gained a bunch of skills, and then provided a justification that we could go after and build sponsor funding from that, which I did. Like we had some pretty robust programs after that. We also can use LDRD to build these larger things called initiatives, which I'll talk about here in a second. But the idea here being is that we have these objectives, these things that we're strong at. We can build research programs internally around that, where we direct where that funding goes and can build for the future. Why that's important for this conversation is that LDRDs are an excellent way for us to partner with academia, because the money is super flexible. We don't have to go to a sponsor after the fact and mother may I our way into getting a subcontract set up with A&M. We just set up an agreement and away, and money gets sent and we're off. It's also a thing that we often use these, and I'll talk about this later, as a way of bringing in speakers. So if there's a topic of mutual interest, we can do that as well. So I'll get into that in a little bit. So can move on.
So the LDRD, each lab run its own LDRD, like 3 or 4 LDRD per year.
It depends on the level. So there's multiple levels. There's our large scale initiatives, which are 3 to 5 year research programs, and there are about 3 to 4 of those every year. We have agile investments, and this is generally the same across all of the labs. We have agile investments, but usually there's like 1 or 2 of these. They're usually like a year to year type of a thing. And then we have seed LDRDs, which are individual projects. I was funded at like $250K a year for 2 years types of deals. And then we have other strategic elements like these things that we call directorate objectives, where we think we're not even going to do research now. We just want to think like, how does P&L fit into these problems? And I can give some examples of that. Like we have one around misinformation, one around some RF and machine learning stuff. But yeah, does that answer your question? Yeah. So at the lab, we have 4 research directorates, and they just generally fall. There is some overlap between each of these different directorates. And I like for one, I know a lot of people on our energy and environment directorate, although I don't really work with them. But I do have some intersections with our physical and computational sciences directorate. This is where all of our math people are, like fundamental math folks reside. And so, you can think about each one of these as owning like different use cases. So energy, environment, and it's pretty self-explanatory. Earth biological systems, and then I'm in the National Security Directorate, and our use cases sort of span across a number of these different ones. But while we have different use cases within each of these directorates, there's still a computational need, mathematical need, machine learning need, and shared across each of these. Pardon me. Okay. And in case you're not familiar, TRL stands for technical readiness level. It basically just indicates the research maturity. Me and NSD, I work on more applied problems, where some of the other research directorates focus on more fundamental things. If you ever come visit P&L, I'd be happy to show you any of these facilities. We are the only, it's part of Energy National Lab that owns our own marine sciences laboratory. So we have a facility at the Bay up at SWIM in Washington, where we can conduct research in all sorts of different maritime applications. And then we have the only other one I'll mention here is the Environmental Molecular Sciences Laboratory. This is a really cool facility. I love going there. I just like walk the halls. They've got like all the posters of the research that they're working on. I have no idea what they're talking about, but it all looks very impressive. These are instruments that are one of less than 5 in the world, like giant magnets, giant electron microscopes, all sorts of really cool stuff. It's a user facility, so researchers from all over the world can propose to use these, and they get those proposals can get granted. They come out for 6 months and run a bunch of experiments, and it's all very interesting work. I've done some work with some of our material scientists, for example, that work over at IMSL. They were looking at, for example, they have these scanning electron microscopy images where they're looking at material changes through different phases under different catalysts, right? And they want to predict, what is the property of this material as it goes through these phase changes? Can we use some form of deep learning to estimate what these structures will look like at the end of this process? That was interesting. And then we're also building out some other stuff as well. Important people past this. Okay. So strategic elements, research elements at the lab exist at multiple levels. The highest level here is what's called our lab objectives. And these are generally capabilities that are relevant across the entire lab. And that's some really fundamental research. So something like coastal ecosystems, obviously this involves work up SQUIM. Grid decarbonization is stewarded by our energy and environment directive because of the energy push there. And then we have a thing like machine reasoning, which covers a lot of different work. For example, there is some fundamental work in the mathematics of machine learning, and some of those efforts get funded under that machine reasoning initiative. There's also some questions around compute, hybrid architectures for training and deploying machine learning models. That would also fall under a laboratory objective like this. DOE, Office of Science, is very interested in how they can leverage their big iron HPC systems to train the next generation of models. And so this is an opportunity for us to align some of our research with their strategic objectives as well. And then we also have directorate level objectives, investments. And these are high level research opportunities that are a little bit some which are a little bit more focused. They're usually stewarded by a particular directorate with engagement with some of the other directorates, but this is the core piece of how we fund projects, internally fund research projects. I will draw your attention to two. Well, actually, we can talk through most of these. There's some work in some of our partnerships with industries such as Samanova, which there's a picture of that machine there under the infrastructure early production AI architectures graphic right there, where we're looking at, okay, well, what do these purpose-built hardware architectures provide in terms of allowing us to build specific models or explore specific research questions. An example of one of those is we have a researcher who's very interested in neural architecture search, right? So it's okay, well, I'm going to model, a neural network as this, directed graph, and then I'm just going to perturb this thing a whole bunch, and we'll just see what falls out of this architecture piece. And he was able to use the Samanova machines to do that more efficiently than he would under traditional compute. So the other two that are more relevant here is one is this data model convergence piece, which is looking at how do you do hardware, software, data, code, co-design of these large-scale machine learning systems. And then I'll get into this other one here in a second called MARS, which is the mathematics for artificial reasoning for science. So in MARS, a lot of our work in science-inspired or physics-informed machine learning, that can sit in that area as well. That is an interesting initiative in that it's brought together like domain experts in these different scientific problems, but also more traditional AI researchers, like structured knowledge types with pure data-driven approaches like neural networks. It's like, okay, well, how can we like take the best of all of these things in order to solve problems faster?
So Mike,
Yes,
what
sir.
is that the operations to research?
Oh yeah, of course. So, I mean, we're a research institute, obviously, but we have a fairly robust operations component as well, because the lab needs to function, right? The lights need to turn on, the network needs to be working, and the HPC needs to be on. So the operations side of the house provides very rich sets of data and use cases that we should be able to use to answer research problems. So for example, what sort of questions could you answer if you had prox logs for a building or for a campus, right? You could probably do some like interesting spatiotemporal analysis of those types of data. You could also do some interesting work if you had access to like network plugins. And so this is really focused on making available some of that operational data for research tasks. That's like eat your own dog food with respect to, and then the other way around too, for developing tools that help us understand cyber data, for example, can we push that to the operational side of the house, have them like use that? So.
Are you aware of there's an academic field, it's called operations research?
Yes, so we have some.
It's not the whatever the title over there is not really tailored for the OR, right?
Right. So we have a group of folks that do traditional operations research type of work. They're in our statistics, they're on our stat side of the house, but this is not that.
Okay.
Yeah. So I'm trying to specifically call out things that are relevant to the data science and mathematics side for this conversation. So there are three things here. I'll start on the right. MCPC, which is our materials characterization, prediction, and control. Characterization, prediction, and control are classic machine learning style problems. So this is an agile investment. Now the point of an agile investment is to be extremely flexible in terms of the problems that we go after and the ways in which we go after those problems. So for example, we had an agile investment a couple of years ago called Deep Science that was focused on bringing together a data scientist and a domain scientist and giving them 6 months to solve a problem together. Some of these longer term investments such as Mars, these are years, 3 to 5 years worth of an investment in something. You can really go after a big problem in that time. The point of an agile is not to go after the big problem. It's just to get some initial work done. Mega AI, well, okay, I'll go to Mars. Mars, we talked a little bit about this. This is the artificial reasoning and science work where they're looking at building systems that are fieldable and assured. So for example, if you've done any work with large scale language models, you'll know that you can probe these models to generate generate text based on a prompt, right? Or do abstractive summarization over a large corpus of text, right? And that's all very interesting. But if you ask a model to do like an abstractive summarization, how do you evaluate the truthfulness of what was produced, right? Is this just like model gibberish, or is there some way to assess like how much you can trust that model? So they're doing some work in that area. Mega AI is really looking at that foundational model. So large scale language models and their equivalent for other modalities, specifically for science and security applications. So in other words, it's great that you can build a large scale language model on Wikipedia and Reddit, and those are really good, right? You can fine tune that thing to work on whatever sort of data domain that you're interested in. But if you are a material scientist or a chemist, say you're a chemist, and you want to leverage some of the knowledge that you can gain from these large scale language models, is it really, are you really going to get the full bang if you just like fine tune BERT on a bunch of abstracts from chemistry publications, right? Well, maybe, but maybe not. Maybe there are some domain specific subtleties to the ways in which chemists talk about chemistry that you want to build into the model ahead of time. And furthermore, there are other canonical data sets in this field in analytical chemistry that you may want to take advantage of, like the SMILES data for like compound identification, right? You want to be able to pull that in. Now we start getting into like a multimodal space. And so they're thinking about, okay, how do we build very large multimodal models to aid in scientific discovery? That all sounds well and good, and that's a very interesting research problem, but soon you come across all sorts of challenges with that, right? Like, well, how do you assess that model? Like if you build like a multimodal analytic chemistry language model, like how do you know whether it's actually doing anything good or not? Like, are the benchmarks good enough as they exist, or do we need to make some sort of improvement? That's the whole point of these investments, is not to go in there and say like, pardon me, here is the one specific problem we're solving. We're like, hey, this is a thing that could be useful. What are all the different research questions that we can answer in that? This is why, too, the LDRDs make for great partnership opportunities with universities, because just as soon as you dive into some of these problems, you see all these little tributaries like sprouting out into questions that need to be answered. Chances are one of our academic partners are working on one of those things. We can partner with them and bring that together. Excuse me. I need to get more talks or something. So we have a number of partnerships. We love working with the other labs. The nice thing about how DOE has the National Lab Complex set up is, well, there might be overlap in some areas. You know, we really do offer different things, and so that makes for great partnership opportunities. We have great relationships with industry, which allows us to really go after problems that help them, but also are things that we're interested in. We're involved in various academic alliances. We publish. We get out there in a number of different mechanisms as well. So we have a we have a mandate to work publicly in our research. So I'm going to get into some specifics of our AI machine learning work. I'm going to skip some of these things. If I talk too fast through a slide, it's probably because I don't understand the science. But if you see something that's interesting and you want to know more, I know the people who do all of this. So when I started at the lab in 2010, I was doing computer vision research, and my first task was a re-implementation of David Lowe's 2003 SIFT paper for image retrieval thing. So this is like SIFT and SVMs, right? Obviously, as you start to get into the mid 2010s and neural networks make some resurgence, all of that sort of stuff is all of my previous work completely irrelevant. But as a lab, we noticed that there are opportunities for us to take this like surge of deep learning and apply it to these other areas and learn some interesting things. So we had some internal investments in AI and deep learning that I had been involved in various degrees prior to FY17, but in FY17 we kicked off this deep science investment where we paired data scientists with domain scientists. We asked our data scientists and our domain scientists to pick a specific problem within any sort of science area, see what we can do to solve it. I'll talk about a couple of those here coming up.
So Mike, I find interesting on the energy part and how two problems, they are so different from each other, right? I mean, two organizations are almost like the entirely amount from
Yeah.
the radiation signal, that's entirely a kind of physics problem.
This is a very interesting. You're the first person. I've probably given this talk probably 100 times. You're the first person to mention that, and you're absolutely right. And when I think of like the radiation sickness work that was done here, that was very like narrowly scoped thing. Someone had a data set, someone had a problem, they wanted to solve that thing. Grade control and optimization is not my area of expertise, but from what I understand, this is a humongous, like a gigantic research area, multidisciplinary as well, right? And in this case, the idea was like, okay, well, let's pick a problem within that control space and apply it to some grid data through some partnerships. I don't fully understand, and go after that. So yeah, you're absolutely right. Like, but that does show like the span of the problem.
How does the DOE labs kind of differentiate, the grid control optimization seems to be a problem also very much belongs to aerial, right? Because they are the labs in charge of, a lot of this kind of energy production also forth.
Sure.
I suppose there must be a lot of collaboration, but is the DOE kind of concerned about this type of overlapping type of thing?
Yeah, I mean, I won't speak for DOE, but I will say in the ways in which we interact with DOE, like DOE is for our internal, like all of DOE is aware of all of our work that comes in. They have to approve our funding packages, and they keep aware of stuff like this. But our internal investments, especially, we basically propose to DOE, say this is the work that we want to do on these internal funds. And they say yes or no. Obviously, it's a more complicated process than that, but that's essentially what it boils down to. So yeah, there are areas in which there's overlap, but I would say those are more collaboration opportunities rather than competitive opportunities. Like we're not involved, as far as I know, on anything on the production side of the house. I mean, that's a whole other area. There are other labs that own that piece. But from an analytics standpoint, from a monitoring, that is where we sort of distinguish ourselves in some regard, and how we stay on the right side of the line with respect to not duplicating work done in other labs. Does that answer your?
Sure. I worked with aerial quite a lot. Of course, only with one. So I'm really familiar with many of the things.
Oh, good. Yeah. Yeah, and we've had some partnerships that I've been involved in with like Sandia, where at first blush, like, well, it's kind of doing the same thing. You get into the conversation, you realize like, oh, we're attacking these problems from two different sides. In this particular case, like they were doing a lot of work in like simulation that I wasn't doing either, simulation, but I was more focused on like the data side. It's like, oh well, that's actually like a really good opportunity for us to work together. AI P&L today. I mean, I think we've got a ton of folks doing this work. Our main campus is in Richland. We have a secondary campus in Seattle. It's a very interesting place to have campus in terms of like the tech talent for sure. We have got, it says about 200 plus people doing new methods. That's probably accurate. The third bullet is really where I like to draw attention to. 2017, he's like tier 1, top tier conference. We weren't publishing it. We just didn't, like 6 doesn't, that's rounds to 0 basically, right? And since then, though, we've been able to get some of our work in some places that we're fairly proud of. I remember when I started at the lab, I was like, I'm going to publish CVPR. I don't care if it's a workshop. I'm going to publish a CVPR. They're like, no, that's never going to happen. That's not the type of work that we do. And papers at CVPR workshops 2 years in a row. Yes, it's a workshop. It's not a main conference. I understand that's not my focus, but like I tell that just to like give you an indication of how the mentality has shifted. And again, this is where our academic partners really come into play, because we are starting to go after the types of problems that are worthy of publication. Oh, we have some pretty nice lab-wide compute infrastructure too. So that's mostly relevant in terms of like we have great relations with like the cloud companies, AWS, Google, Azure, but we also have our own GPU compute systems as well. Yes, we have the infrastructure. We've worked really hard to overcome the talent gap. Some of that has been retraining. That's a picture of me training about 50 of our staff in deep learning 3 or 4 years ago. I'm wearing a different shirt. Yeah, I'm wearing a different shirt. But we've trained over 300 of our staff through our boot camps, and obviously going after different recruitment strategies. All right, so I am going to sort of hit the highlights of these last few slides here. I think that one of the things that we recognized early on was that AI is such a catch-all term. Can mean a lot of different things, a lot of different settings, but it's also the type of thing where I remember I encountered this probably more, honestly, it still happens, but like around like the 2017, 2018 timeframe, like it became such an amazing buzzword. It didn't mean anything, right? You could say you're doing AI, but and so for us, it was like, okay, well, we have to be specific about what we're going to focus on because we're not going to do everything. We might touch on certain things that we find interesting. Like for a while there, I was really interested in like self-supervised learning for image representation. I was like, that's great, but that's not a strategic element. It's not a thing that we like hang our reputation on as a lab. So we want to be very clear in what we consider ourselves good at. So this idea of scalable, assured, and fieldable AI is really where we're hanging a lot of our research elements on. I'll get into each one of these. But first, so within that sort of framework, we have these 4 ideas that we talk about. It's like, okay, if we're going to be good at something in AI, it's going to be one of these 4 things. One of the first is learning with limited data. I would also sort of lump image retrieval systems in with limited data, but really what we're talking about here is building like metric learning systems and small data classification systems around little data. Domain aware AI is like the physics informed, science informed machine learning work. Assured and trustworthy AI. Going back to the previous slide, we've done some work in like understanding like you're treating AI the same way that you might treat like software assurance, right? What are inputs that cause a model to fail? How generalizable are your models to various inputs, et cetera? And then more on the engineering side, but we've done some work in like scalable AI architecture. And so those 4 thrusts sort of underpin what some of our internal efforts. We want to like tie our internal research efforts to one of those 3 thrust areas. So I'm touching on a couple of these. There's some architectures work with ARIA. I don't know a ton about physics informed the physics informed learning machines. I don't know much about that. Machine learning test and evaluation was born out of a lot of work that we've done with DARPA over the years in building systems that allow for T&E and B&B of these machine learning systems, also with like a visual analytics slant to that as well. So if you're gonna, it's not enough to say like, oh well, your cat and dog classifier, your mislabeled this chihuahua as a cat, right? You have to, like, what are you gonna, how are you providing that information back to the user in such a way that they can make a different decision, basically? It's like your data scientist can build a better model, or your analyst knows how to interpret information. All right, so I've got a couple slides here where I just talk in generalities about some of the work that we've done. This is some interesting work in chemical compound, standards-free chemical compound identification using mass spec data. So this was funded out of our deep science agile investment, and they wanted to use some deep neural networks on some mass spec data to reduce the error rate in some of their compound identification work. They were able to do so much faster than some of the first principles methods that were previously involved. Ryan Renslow was the PI of this effort, and that work is really well. We've done some work in, this brings together some visual analytics systems as well as our learning with limited data. So how can you build like an interactive system to make sense out of large amounts of data? So if you've got a user who's moving things around, can the machine learn from those groups, etc. This gets into some of the grid control work that we had briefly touched upon. There are a couple efforts that were involved in, I would say, just general control and optimization problems for energy. This one is deep grid, is more like a grid one. There's a buildings one that was really interesting that used like reinforcement learning to develop like a policy for different equipment in the building to optimize some usage function. But the deep grid work, which is linked in our news release there below, was really looking at emergency recovery scenarios and using machine learning to inject controls at various levels. That was interesting. Yeah, we did some work in the molecular structure of these water samples. It seemed interesting, but I don't really know a lot about that, to be honest. I was involved in this project, and this was super cool. So we have a fundamental physics thrust as well when we were looking at how do we partner with some of these international organizations to, solve some fairly aggressive physics problems. And so this was a neutrino physics problem where we have there's these laboratories that have these like giant tanks with the fluid in them. And they're like, a couple kilometers. They're in like facilities that are a kilometer under the surface. And so a neutrino will pass through pretty much anything, right? Whereas some of these heavier particles this is why it's in the Earth, so that these other particles don't interact with this fluid. But they're looking for these interactions, right? And so what happens is like they're looking for a particle that will interact with the fluid in these tanks, which causes a bubble to be created. Tanks compress, bubble pops. There's an audio signature, it's camera signature. It's also a system. So they were saying like, okay, well, we need to like calibrate these things, and how they do that is they put different sources around these tanks and cause different particles to interact and all this sort of stuff. And we were looking at building methods that would take in the different inputs from either the audio, basically from the popping of the bubble, or some visual data as well. Say like, oh, what was the source that produced this interaction? And it was really fun. We got to go up to Snow Lab in Canada and visit there. It's an active minerals mine. I got to dress up in full like miner gear and take a elevator down 2 kilometers under the earth and see some really cool science work. So that was interesting. That's involved in international partnerships as well. I touched on this a little bit with the operations and research stuff. But living labs are the things, right? Like a lot of universities, I think I've talked with Ron Tao about some work that he's been doing and some living laboratory stuff here as well as in elsewhere on campus. But P&L, we've set something like that up as well. So this makes this, we provide through our data stewardship board and our data mart the ability to basically wash data that comes out of our operational systems, like de-identify them or anonymize the data. Sorry, not the opposite of that. We want to anonymize the data, strip out anything that's not like research useful, and make up that data available for research. And that's data that we can, with approval, share with partners and stuff. And then since coming across 10 minutes, I'll just fire through these. We've done visual analytics work for close to 40 years. It's one of the things that we're fairly well known for. And we've got some interesting systems built. Thusly, oops, apologies. Data science side, we're pretty much on the applied end of that spectrum. We try to pull in research as necessary, but we work very closely with like our cloud engineers and software engineers, not only say like, hey, let's build like a really interesting, entity disambiguation model for text. Like that's an interesting problem, but let's build like the cloud infrastructure around that so that it can actually be used and exists as more than just like a PyTorch model. And then we got some work in cyber grid security. So this is pulling together our cyber folks with our energy and environment folks. So not only providing like cyber assessment of facilities, but also cyber situational awareness, test beds such as CyberNet and PowerNet for bringing in new equipment into simulation environments, testing out like cyber footprints, pulling data off of those instruments in a quasi-simulation style environment that we can then use for research. And I'll just advanced manufacturing. This is a fun project. If you ever come visit PNL, I would love to show you our fish lab. So we build these like, they want to monitor, so this is in Eastern Washington, right? So fish migration is the thing out there. And so they have these like tiny sensors that are basically just like these micro battery systems with like a little bit of compute. And they stick them into fish, and they use that to monitor like how many fish are making it through the dams, how many fish are getting eaten, how many fish are successfully making it to like their mating area. It's really fun work. Like it's so fun talking to the researchers that do this work. You can come up and you can see our lab where we grow the fish and stick them with the batteries. They don't mind too much. I'll just skip past that since we already talked about some of our test bed capabilities. So as I mentioned at the very beginning, I'm a P&L staff, but I'm on joint appointment here at A&M. I really just want to meet people and hear what their research problems are and find out opportunities for us to collaborate on things together. I moved down here. I bought a house in Bryan. Like I'm going to be here fairly permanently. I really want to build out some partnerships, whatever that takes. I think that our internal investments are a great way for us to work together. I'd love to bring folks out to P&L to give a talk on their research, talk to our research. It's a fairly low stress environment. We're not working on a proposal together yet. We're just talking about fun science stuff, and then work on maybe work on some proposal opportunities as well. I've been involved in several since I moved down here a little over a year ago, and we can do some more. I see I have a typo in my slide here, but it should be joint ML ops, deep learning workshops and training. I know that TAMIDS has a lot of training and education opportunities. P&L, we have done the same or similar with some of our AI and deep learning workshop, and there should be some opportunities for us to collaborate on that. We already do so with industry. We work with like AWS on some of our materials there. There may be some opportunities to do some cool stuff there. Collaborations, and then, well, I have a list of people who are very excited to talk to folks down here. I've got actually a friend at P&L who's applying for a admission in the online master's program within the EE program. And then, just setting up some various workshops and seminar speakers and such. These are opportunities for us to work together. So I'm here as a resource. I'm here to represent, jointly P&L and A&M, and whatever I can do to be helpful, even if it's just like having an interesting conversation about work. That's what I'm here for. So thank you very much for the opportunity to chat today, and I look forward to having more conversations on this in the future. So thank you.